Pluto is a far-off and enigmatic dwarf planet that was once considered part of our solar system's planetary family. However, recent shocking statements from prominent astrophysicists Neil deGrasse, Tyson and Michio Kaku have brought Pluto back into focus with an astonishing announcement. They claim that this frozen world may be on a potential collision course with Neptune. But how could this occur, and what would the consequences of such a massive event be? Are we witnessing an unusual astronomical event, or is there something deeper at play with this approaching cosmic collision? Join us as we delve into the possibilities of a Pluton-Neptune impact. Pluto, a former planet that was downgraded to a dwarf planet in part due to its peculiar orbit, continues to be an object of intrigue and study in the scientific community. According to recent predictions from leading experts, Pluto's trajectory is dangerously close to Neptune's. Astrophysicists Neil deGrasse, Tyson and Michio Kaku are raising concerns about a potential catastrophic collision between these two planets, which could pose a significant threat to Earth. How is such an event even possible? Pluto's voyage around the Sun is unlike any other planet in our solar system. It takes an extraordinary 248 years to complete just one orbit. Since its discovery in 1930, Pluto has not even finished a single full revolution. But the intrigue doesn't end there. Pluto's orbit is characterized by its highly elongated shape, which diverges considerably from the nearly circular paths of the major planets. What makes Pluto's orbit even more fascinating is its tilt, set at 17 degrees relative to the ecliptic plane. Its path is much steeper compared to the other planets. This tilt and elliptical nature add complexity to its orbital motion. One of the most captivating aspects of Pluto's orbit is its intersection with Neptune. For roughly 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, challenging our understanding of their relative positions in the solar system. This raises the inevitable question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The analysis of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to interpret its unique path. Unlike the other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out with its steep tilt and elongated shape. The puzzle deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amid these complexities illustrates the intricate nature of celestial mechanics. The three-body problem in space involves predicting the movement of three objects, like Pluto, Neptune, and the Sun, as they interact through gravity. It's akin to predicting their future positions based on their starting points and the gravitational forces acting between them. In Pluto's case, this problem reveals how its path, Neptune's orbit, and the Sun's gravity interact in an intricate way. The terms omolibration and latitude libration, along with the VZK oscillation, are part of this puzzle. According to astrophysicists, the reason Pluto's orbit doesn't intersect Neptune's more dangerously is because of azimuth libration in the context of Pluto and Neptune. This means that when Pluto crosses Neptune's orbit, it's always positioned at least 90 degrees away from Neptune. This spatial separation is vital in preventing their paths from colliding. Latitude libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes close to Neptune or any other massive planet, it's situated considerably above their orbital plane, offering an extra layer of protection from potential collisions. Another critical factor in this equation is the VZK oscillation, named after three scientists, V, Zell, and Kai, who studied the way objects move in space. It involves the interaction between three space bodies such as Pluto, Neptune, and the Sun, whose gravitational forces pull on each other, affecting their movements. In Pluto's case, the VZK oscillation helps us comprehend why its orbit around the Sun is so unique. Even though Pluto's path seems irregular, this oscillation keeps it moving smoothly over long periods. The VZK oscillation suggests that even though space appears chaotic, some underlying rules help keep everything in harmony. These various factors help stabilize Pluto's orbit, ensuring it doesn't collide with Neptune or veer off course. This three-body problem is essential for understanding how orbital paths can change due to the gravitational pull of nearby celestial objects. Investigating this issue provides deeper insights into Pluto, our solar system, and distant worlds. In the late 1980s, numerical simulations revealed that despite these stabilizing mechanisms, Pluto's orbit is technically chaotic, with small variations in initial conditions leading to significant differences over millions of years. However, these unique aspects of Pluto's orbit have been shown to maintain stability over incredibly long time scales, essentially keeping the chaos at bay. Recent computer models have improved our understanding of how major planets like Neptune, Jupiter, and Saturn affect Pluto's motion around the Sun. Neptune and Pluto are locked in a special resonance where, for every 2 orbits Pluto completes, Neptune completes 3. This resonance ensures that Pluto's path remains stable, but Neptune isn't the only planet contributing to Pluto's stability. Jupiter's gravity also plays a significant role, and Saturn's influence adds some stability as well. These simulations demonstrate that Jupiter's gravity alone is strong enough to ensure Pluto remains on a steady course for billions of years. It's as though Neptune, Jupiter, and Saturn are working together to keep Pluto safely in orbit, preventing it from veering off track. These phenomena are crucial for maintaining order and predictability in space. Without such mechanisms, the solar system would be a far more chaotic and unpredictable place. Objects like Pluto could collide with others or be ejected from their stable orbits, causing a cascade of changes through the solar system. For Pluto especially, given recent discussions about a potential collision with Neptune in the future, understanding its orbit is key. This helps us appreciate the dynamic nature of our solar system. Pluto's case highlights how even the most seemingly erratic orbits can achieve stability through the complex interplay of gravitational forces and orbital mechanics. It also underscores the importance of continuous observation and study of these phenomena to deepen our understanding of the universe. Investigating the far reaches of space often requires us to confront the unpredictable behavior of celestial bodies, and Pluto's orbit is a perfect example of such unpredictability. The concept of orbital chaos, where the precise path of a celestial body can be highly sensitive to initial conditions, is clearly demonstrated by Pluto. This means that even small changes in Pluto's position or speed can dramatically alter its long-term orbit. Computer simulations have been invaluable in helping scientists understand how Pluto moves through space. These simulations use sophisticated mathematics to model how Pluto and other celestial objects like Neptune interact with one another. By tweaking small details in the simulations, astronomers can see how these adjustments might dramatically shift Pluto's trajectory. Back in the late 1980s, these simulations revealed that despite Pluto's stabilizing features like azimuth and latitude libration, its orbit can still be highly unpredictable. A slight change in Pluto's position or velocity could result in a vastly different path over millions of years. Even with these chaotic tendencies, Pluto's orbit remains stable over immense periods like billions of years. This suggests that there is an underlying order to its seemingly erratic path, predicting cosmic events, especially those involving chaotic orbits like Pluto, is a significant challenge. The inherent unpredictability of these systems means that long-term forecasts are often fraught with uncertainties, while numerical simulations offer powerful tools for understanding the future paths of celestial bodies. They also demonstrate the limitations of our ability to make precise predictions. These models are highly dependent on the accuracy of initial conditions, and even small errors or oversimplifications can lead to drastically different outcomes, making exact predictions a difficult task. Moreover, the chaotic nature of Pluto's orbit reminds us of the ever-evolving and dynamic universe. While we have made tremendous progress in understanding space, the case of Pluto reminds us how much still remains unknown. Studying the gravitational influence of the gas giants on Pluto's orbit provides valuable insights into the broader mechanics of our solar system. It reveals how the position and presence of each planet can have wide-reaching effects on the stability and trajectory of other bodies within the system. So why are major astrophysicists raising alarms about a potential collision between Pluto and Neptune only now, despite all these forces working to prevent such an event? Neil deGrasse Tyson, a leading astrophysicist and key figure in the reclassification of Pluto as a dwarf planet, offers a unique perspective on the mysteries of our solar system, particularly regarding Pluto. Tyson, widely recognized for his role in demoting Pluto, suggests that this change was not a step backward but a necessary update as our understanding of the universe grows. He views the reclassification as an adjustment to reflect the increasing knowledge of the countless bodies orbiting our Sun. Tyson's approach to the study of celestial mechanics is one of ongoing learning and adaptation. He believes that the complexities of orbits like Pluto's serve as a reminder of how much remains to be discovered in space. The allure of these unknowns is what makes astronomy so compelling. From his perspective, the prediction of a Pluton-Neptune collision is based on evolving models of the cosmos and the inherent uncertainties that come with studying celestial bodies over vast periods. But here's the catch. As far as Tyson and other astronomers can tell, such a collision is highly unlikely in the near future. While Pluto's orbital dynamics are chaotic, they remain stable enough that we shouldn't worry about an impact anytime soon. However, this doesn't mean the possibility of a collision is entirely ruled out. New discoveries and updates to our models could change our understanding of Pluto's future trajectory. Likewise, Michio Kaku, a renowned theoretical physicist, acknowledges that a Pluto-Neptune collision is possible, but likely millions of years away. Kaku, who frequently explores the broader forces that shape celestial bodies, reminds us that the universe operates on time scales far beyond our human comprehension. In conclusion, while Pluto's fate remains uncertain over immense time periods, its current position in the cosmos is stable and predictable. This knowledge, however, should not dampen our fascination with the mysteries of space. Every new discovery and insight adds to the awe and wonder that drive our ongoing quest for cosmic knowledge.